Today we'll be going over lesson 3.06, Another Day. So today's objective is I can model a vertical shift of a function in 2 out of 2 problems. And we will start with a story. So every day when Rashid's mother comes home from work, he asks her how her day was, and she says, "Another day, another dollar." Being a mathematical thinker, Rashid starts imagining the function that would model his mother's saying. So we're thinking, each day we get another dollar. So his thinking goes, on day 0, she hasn't worked yet, so she has $0. On day 1, she works and gets $1. On day 2, she gets another dollar, so now she has $2 total. On day 3, she gets another dollar, so $3 total. So this is the graph that results. We have days down here, dollars up here. Day 0, we had 0. Day 1, we have $1. Day 2, we have $2, and so on. So what is the equation for this graph? It says, what's the equation for this discrete function? So we know it's discrete because we've got dots that are separated. And then it's a function because it passes the vertical line test. How do we find an equation for it? Well, we note that this is a straight line. And our form for a straight line is always mx plus b, that slope-intercept form. So we just need to find the slope and the intercept. Slope, we can tell, goes up 1, right 1. So rise over run will be 1 over 1, which is 1. And then our y-intercept is 0. That's where it crosses the y-axis. So our equation here ends up being 1 times x plus 0. We don't need to write the 0, that doesn't do anything. And then we don't actually need to write the 1 times either. That doesn't do anything, just leaves x. So f of x equals x is our overall equation here. Another way to think of this is just y equals x, right? Every time we have an x value, we get the same y value. So 0, 0, 1, 1. This one's 5, 5 up here, 7, 7, and so on. So Rashid thought some more, and he wondered what would happen to his function if he started with $5 on day 0 and then earned $1 a day. So now we're thinking, well, maybe we'll have some money in savings first. We'll have days 1, 2, 3, and 4. We're going to try to model this with a table, a graph, and an equation. So if we start with $5, we're adding $1 a day. That takes us up to $6. $7, $8, right? We're just adding $1 a day. We're familiar with these patterns. Add 1, add 1. If we wanted to do the equation, once again, we see that we're adding. This is arithmetic. We know that arithmetic sequences follow linear equation patterns. So when we have an arithmetic sequence, m is our slope, which is our common difference, m is 1. And then b is our value at 0. There it is, right there at 5. So our equation now will be g of x equals 1 times x plus 5. Or we might just write that as x plus 5, since 1 times anything is itself. We can graph these points. 0, 5 is here, 1, 6 is there, 2, 7, 3, 8, 4, 9, and so on. We will continue on with this line. We've named this g of x. So now let's compare those two functions and see what happened. This was our original function, f of x equals x, and this is our new function here. We call this g of x equals x plus 5. asking, how did the function change? What happened to the function here? So if we look at, say, the y-intercept and the y-intercept here, how did that change on the graph? We started with this dot, we ended with this dot. It looks like it moved up, and it went up 1, 2, 3, 4, 5 units. So it looks like it went up 5 units. If we take any other day, the point on any other day, say maybe this one, and see how it changed, we go up 1, 2, 3, 4, 5. Looks like that one also went up 5. Or this one goes up 1, 2, 3, 4, 5. So it looks like every single day, the dot that results moved up 5. And notice this is what the equation was. Moved up 5. Let's look at another addition to this story. So Rashid thought about all the bills that his family needed to pay. What if the situation changed so that on day 0 they owed $10? So instead of having money in savings, they were actually in debt, and then they added $1 a day from there. We could model this again with our table. We start with -10 on day 0. We're going to add $1 each day. -10 plus 1 is -9. Plus 1 is -8. Then -7. Then -6. We can graph these points. 0, -10 is down here. Then 1, -9. 2, -8. 3, -7. 4, -6, and it looks like this pattern is going to continue as a straight line. We can write our equation. Once again, this is a straight line, so it's going to be mx plus b. Our slope hasn't changed. That just continues to be +1. But our y-intercept has changed now. Our y-intercept is now -10. So our overall equation here is going to be 1 times x plus -10. Or we might write that simply as x minus 10. So here are all the graphs on the same, or all the functions on the same graph. Here's our original one, f of x. And then we started with $5, there's g of x, and then we started with -$10, we started in debt. If we look at the original to the case where we started in debt, how did that one change? We look at the y-intercept to the y-intercept, what happened to that? Well, looks like it went down, and it went down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. We went down 10. Is that going to be true for these other dots? Let's see. Let's try this one. Go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like it is. We went down 10 there. Maybe this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. It looks like all of these go down 10. And here's the equation we used, x minus 10. Remember up here we went up 5, and we used the equation x plus 5. So do you notice a pattern there? What do you think happens when you add a particular number to a function? So if we just have some function over here, let's call it r of x, and we shift it up any particular number, let's say 9, what do you think happens? I think I just answered it for you actually. It goes up 9 units. So we added 9, and that made the graph go up 9 units. What if we subtracted 9 instead? What would you expect to happen there? I think this might be confusing that I drew a little hyphen. If we subtract 9, now it's going to go down 9 units. Right? This is the same number we subtracted and it went down. The same number we added and went up that number of units. So we can actually generalize this to functions, all kinds of functions. When you add or subtract a number to the function, it shifts it up or down respectively. If you add a number, like over here, if we add 2, we have h of x and we added 2 to it, now each point on the function is going to be shifted up 2. This one goes up 2, this point would go up 2 here, all the points would be shifted up 2. The whole graph would move up 2 units. Or if we subtract a number, like down here, g of x, this is going to be shifted down 3 units. So we start here and go down 1, 2, 3, go down 1, 2, 3 here. This one would go down 1, 2, 3. Any point you pick on the original function, we would take it down 1, 2, 3 because we subtracted 3 from it. So when you shift a function around like that, you can move it up and down. It turns out there's a way to move it left and right as well. We're just not going to talk about that today. The parent function is the function we start with initially. So we can start with any function, and we can move it around the graph. Notice this black function can be moved up to create this blue function, can be moved to the right to create this green function, or can be moved down and left to create this red function. All of these functions have something in common. They started with this one, so we call them a function family. They have a lot in common. We've basically just moved them somewhere around the graph. We've moved them up, or left, or down, or right. Or maybe we've moved them a couple of directions. So we call that a function family. So let's look at a couple of examples of shifting a function vertically. This graph shows the function f of x equals 1/3 x plus 2. Let's see if that's accurate. We start here, find the slope, we go up 1, right 3, our slope is rise over run. So there you go, there's our slope, 1/3. And then our y-intercept is here at 2. So there's our y-intercept. So yes, indeed, this is the graph of that function. On this problem, it says if g of x equals f of x minus 1, they want us to graph x and then graph g of x rather, and then write what is the equation for g of x. Well, let's look at this really quick. F of x minus 1, what does minus 1 do to a graph? What would you expect that to do? Well, we said minus makes it go down, and 1 is the number of units, so down 1 unit. So we can take any point here and move it down 1 unit. Move it down here, down 1, move this one down 1, and then we could draw a straight line between them. And this program doesn't love to draw straight lines, but you kind of get the idea. So we have another line now. It has the same slope, right? We still have up 1 over 3. So it has the same slope, but now has a different y-intercept. The y-intercept has been moved down 1. So that's our graph of g of x. What is the equation for g of x? We have a couple ways we could find this. First of all, we could just look at this graph and say, well, it has a slope of 1/3, and it has a y-intercept of 1. So we know we could write g of x equals 1/3 x plus 1. That's our slope-intercept form. But another way we could think about this is algebraically. We could actually use this equation right here, g of x equals f of x minus 1, and we can plug in these values for f of x. Basically, you think of f of x as a variable, right? Remember we said we could think of this as y? So now we're plugging all this stuff in for y. We get g of x equals f of x minus 1. They told us that in the problem. And now we're going to plug in this stuff for f of x. 1/3 x plus 2. That's our f of x. And then we had a minus 1 after it. Now we can simplify this, right? We don't need the parentheses because we're just adding and subtracting. But we could simplify plus 2 minus 1. 2 minus 1 is just positive 1. So overall, we would get 1/3 x plus 2 minus 1 is going to be plus 1, which you'll notice is the exact same equation we got when we looked at the graph. So this works both algebraically and graphically. You could find the equation either way, whichever way makes more sense to you. We just subtracted 1 from this function because we shifted it down. So let's look at a few examples. Perform a vertical shift of plus 3. They want us to graph the new function and write its equation. Okay, so we're going to take a point on the function and move it up 3. 1, 2, 3. We'll take a point here on the function, move it up 1, 2, 3. We're moving up because this is adding 3. We'll take this point, move it up 1, 2, 3. Notice we can take any point. It doesn't have to be on a place where the integers cross. We could do it with this point, which is kind of about halfway through. 1, 2, 3, be about there. Or this one's pretty close to the line. That'd be 1, 2, 3, maybe about there. Remember what we called this when a graph approaches a line but never reaches it? This was called an asymptote. Even the asymptote moves up 3. So these points are just going to approach this line ever closer. And we can draw our curve here. Something like that. That's what our curve looks like if we move this function 3 units up. So we got the first part, we graphed the new function, now we just need to write its equation. Well, are you ready for this? We moved it 3 up, so we're going to add 3. That's our new function, that's it. We could maybe call it S, or let's go to P. P of x is going to be 2 to the x plus 3. So this would be P of x up here. And this would be R of x. We shifted each point up 3. Each point up 3. And so we took the function, oops, we took the original function. Ah, I can't grab this eraser. Yes, grab the eraser, please. And so we took this original function, r of x equals 2 to the x, and we added 3 to it to shift it 3 up. So that's our new equation. All we did was just add 3 to shift it 3 up. Here's another one. Perform a vertical shift of -4. How would you start this one? We have a graph. We have a function with an equation. We need to graph the new function and write its equation. How would you start this? Did you say we'll take a point and move it 4 down? Yes, I hope you did. We move this down 4. So here's a point on this graph. We're going to move it down 1, 2, 3, 4. Here's another point on the graph. We'll move it down 1, 2, 3, 4. Here's a point. We'll move that down 1, 2, 3, 4. And then we draw a line to connect them. Approximately. There you go. So we've drawn the graph now. This is g of x over here. They gave it to us in the problem. Maybe we'll call this one h of x. What is the equation for h of x? What do we do to shift it down 4? Down 4. Well, if you said -4, that's correct. That's the answer. We subtract 4 to shift it down 4. We can simplify that equation to be 2x. Positive 3 minus 4 is going to be -1. 2x minus 1 is our equation. Notice that matches our graph. We have a y-intercept of -1. And our slope here is still 2. Rise of 2, run of 1. So when we do vertical shifts like this, these end up being parallel lines. What we mean by parallel is that they have the same slope and different y-intercepts. So a vertical shift of a straight line results in a parallel line. Same slope, different y-intercept. So you give this one a try, pause the video, sketch this down on your own paper, or you could even just point at it on the screen, what you would do to shift this graph up 3, right? That's how we would interpret +3. We're going to shift it up 3. Give that a shot, then come back to the video and see if we get the same answer. Okay, so we can start here with a dot and move it up 1, 2, 3. Here. We could start with a dot here, move it up 1, 2, 3. Looks like we have one here, up 1, 2, 3. We could move this one up 1, 2, 3, about there. This one's very close to the line, up 1, 2, 3, almost on the line. And these ones are getting closer and closer and closer to that line. So we have that same asymptote that's moved up 3. There's our asymptote right there. So then we just draw this curve. Something like this. This curve has been moved up 3. Each point goes up 3 units. This one went up 3 units. So there is the graph of our new equation. Our original one was called P of x. Maybe we'd call this new one Q of x. So how do we write an equation for Q of x? Well, we know that Q of x is just P of x shifted 3 up. So we're going to take the equation for P of x and add 3 to shift it 3 up. That's our equation. Now, we've been looking at linear functions and exponential functions. Those are functions we've been looking at a lot this year. Functions we're very familiar with. But there are other kinds of functions, and this actually applies to all of them. You can do vertical shifts on any function. You don't have to be familiar with it. So for example, this is a function called sine of x. This is a trigonometric function. We have not looked at anything like this year, and we actually won't be looking at it. But you can tell it's a function, right? How do you know this is a function? Vertical line test, right? If we have vertical lines, they only pass through once. So this is definitely a function. And it's asking, what do you think this graph would look like? Sine of x plus 2. So this is sine of x, it's showing sine of x plus 2. Knowing what we know about vertical shifts, how would this function change that one? Oh, we know that a plus 2 moves the whole thing up 2. So we just, once again, take any point, move it up 1, 2. Take this point, move it up 1, 2. Take this point and move it up 1, 2. Maybe this point, move it up 1, 2. Take this point, maybe this point, move it up 1, 2. And we'd get a graph that looks the same, but shifted up 2 units. Something kind of like that. Any particular point is shifted up 2 units. And we didn't need to know anything about the sine function to do that. All we need to know is that vertical shifts result from adding or subtracting a number at the end of the function, just adding or subtracting a number by itself. So that wraps up everything for today. I can model a vertical shift of a function in 2 out of 2 problems.